For this video, we're looking at the first derivative test analytically. So we are going to use the first derivative to decide the x values where they're a relative extrema, whether they be minimums or maximums. So the very first thing we're going to do is actually take the first derivative. So f prime of x. And we're going to use the power rule, so I'll multiply it down and then subtract 1 for each exponent. So it'll be 2x squared minus 12x plus 10. And then I want to find my critical numbers. So I'm looking for places where my first derivative is equal to 0 or undefined. There's no place where I'm dividing by x here, so I'm not going to get an undefined value, but I can certainly set this equal to 0. And I'm going to factor this. The first thing I would do is factor out a 2. And then keep factoring into two binomials. So factors of 5 are 5 and 1, and to get a negative 6 I'm going to have x minus 5 and x minus 1. So when I set my factors equal to 0, I get x equals 1 and 5. You ignore the 2, 2 doesn't equal 0. So the next thing I'm going to do is actually draw a number line, and I'm going to put my important numbers on the number line. So my important numbers are my two critical values of 1 and 5. And I'm going to check the sign of f prime of x. So I pick a number to the left of 1, and you can choose any number you like. These are the only two places that the derivative will be equal to 0. So in all 1, 2, 3 of these intervals, it'll either be positive the entire time or negative the entire time. So I choose 0 because it's easy to work with, and I'm going to plug it into the factored form of the derivative. So 2 is positive, 0 minus 5 is a negative, and 0 minus 1 is another negative. So a positive times a negative is positive. If I pick a number between 1 and 5 like 2, I get a positive, then 2 minus 5 is a negative, and 2 minus 1 is a positive. So I have a positive times a positive is negative. A number to the right, you can pick any number you want. I'm going to pick 10. So when I take 10, it's a positive, and 10 minus 1 is definitely positive, so this will be positive. Now, when my first derivative is positive, that means my original function was increasing. So if I thought about my original function, it was going up. It was 0 right here at 1, and then it went down afterwards because my derivative was negative. So I know there's going to be a max at x equals 1. Before 5, it was negative, so you can think your function's going down. Then after 5, it's positive, going back up. So I have a min at x equals 1, and that's what I'm going to write down with my justifications. So f of x has a minimum, at x equals 5. And I know that because f prime of x changes from negative, or you could say less than 0, to positive at x equals 5. Now f of x has a maximum at x equals 1. And I know that because f prime of x changes from positive to negative at x equals 1. So I'm going to do this again, and this time we're making it a little bit more complicated. I put an exponential function e to the 2x. I multiplied it by x plus 3, so when we take the derivative of g of x, we're going to have to use the product rule. So g prime of x equals my first function, x plus 3, times the derivative of the second, which is a 2e to the 2x, that's the chain rule, plus my second function, e to the 2x, times the derivative of the first. Well, the derivative of x plus 1 is just 1, so this is my derivative. Now, if I was again looking for places where this is undefined, I'm not going to find any, but I can certainly set it equal to 0. So I would have, and I'll probably move the 2 up to the front, but 2 times x plus 3 times e to the 2x plus another e to the 2x equals 0. And just like the previous problem, we're going to factor to solve, but what I'm looking for this time is a common factor. And you'll see that the e to the 2x is in both of these terms. So I'm going to factor out the e to the 2x. And what I'm left with is this 2 times x plus 3 plus 1. If I simplify the second factor, I have e to the 2x, and then this is a 2x plus 6, 2 times 3 is 6, plus 1, so this is a 2x plus 7 equals 0. Now e to the 2x never actually equals 0, it's always positive. You can imagine that there's not a value of x that you can plug in that will make this negative. If you plug in a negative, you just get a fraction, a negative exponent changes this to the denominator. 0, 2 times 0, 0, e to the 0 is 1, and then a positive is clearly not a negative. So we can basically just ignore this right now. If I set this factor equal to 0, I get x equals a negative 7/2 as my critical number. So my number line is going to be very easy. I'm only going to have one important number on it, which is a negative 7/2. So I have two intervals where my derivative could be positive or negative, so there's something over here and something over here. You don't worry about the negative 7/2 being hard to deal with because that's not what I'm going to plug into my derivative. I already know that that makes my derivative 0, so I can pick anything to the left of it. So I could pick negative 1,000 if I like. I know that this is positive automatically. 2 times a negative 1,000 plus 7 is clearly negative. So my derivative is negative, which means my original function was decreasing. Over here, and these are the signs of f prime of x. I pick any number I want, like 0. 0 is easy to work with. 2 times 0 plus 7 is positive. So my derivative is positive. My original function was increasing. And you can see that there's a relative min right there. So I would say g of x has a relative min, just 1, at x equals negative 7/2. And I know that because g prime of x changes from negative to positive at x equals negative 7/2. On the next video, there will be one more example where I have to use the quotient rule.